What if I told you that the emptiest space in the universe isn't empty at all? That what we call nothingness is actually a seething, bubbling ocean of energy where particles blink in and out of existence like fireflies in the dark. This is the quantum vacuum, a realm so strange, it defies everything your senses tell you about reality. Picture the fabric of space itself not as a smooth, silent void, but as a turbulent cosmic foam, crackling with hidden activity. Scientists call it the ground state of the universe, but don't let the name fool you. This is where the true magic happens. Think of the quantum vacuum as the ultimate backstage pass to reality. It's where particles borrow energy to exist for fleeting moments, where forces we can't yet explain dance just beyond our reach. And here's the wildest part, this isn't science fiction. These aren't hypothetical guesses. The quantum vacuum is real, measurable, and it might hold the keys to some of the biggest mysteries in physics, from dark energy to the very fate of the cosmos. But the deeper we look, the more questions we uncover. Why does empty space still have energy? How can particles appear from nothing? And what if this so-called vacuum is actually whispering secrets about a multiverse we can't yet see? Over the next 30 mysteries, we're going to peel back the layers of this enigmatic frontier. We'll explore virtual particles that defy time and space, zero-point energy that could power civilizations, and bizarre quantum fluctuations that might rewrite the rules of reality itself. Some of these ideas will bend your mind, others might keep you up at night, but one thing's for certain, by the end, you'll never look at nothing the same way again. So buckle up, we're diving into the quantum abyss where the answers are as strange as the questions and where the vacuum of space is anything but empty. Imagine holding a perfectly still, perfectly empty glass of water. Now peer closer. What seems calm is actually a frenzy of motion, with tiny bubbles constantly forming and vanishing. That's the quantum vacuum for you. It might look like nothingness, but it's actually a cosmic stage where particles perform the ultimate magic trick, appearing and disappearing in the blink of an eye. These aren't just theoretical curiosities, they're called virtual particles, and they're the restless children of the universe's most fundamental law, Heisenberg's uncertainty principle. This principle tells us that on the tiniest scales, nature thrives on unpredictability. Energy can't be pinned down perfectly, and neither can time. So, in the quantum vacuum, particles and their antiparticle twins borrow energy from nowhere, exist for a heartbeat, then vanish back into the void before the universe can even notice. It's like a cosmic loan with no lender and no repayment, just an endless cycle of creation and destruction. But here's the kicker, these fleeting particles leave fingerprints in the real world. Take the Casimir Effect, where two metal plates placed incredibly close together in a vacuum actually get pushed together. Why? Because virtual particles outside the plates exert more pressure than those trapped between them, proof that these ghostly visitors have tangible consequences. Even more mind-bending, some theories suggest black holes might slowly evaporate thanks to virtual particles appearing right at their edges, with one particle falling in and the other escaping as radiation. So next time someone calls space empty, remember, it's more like a simmering soup of possibilities where particles flicker in and out of existence, shaping the very fabric of reality itself. And this is only the first mystery, because if virtual particles can defy logic, what else is the quantum vacuum hiding? But here's where things get even stranger. If you could cool the universe down to absolute zero, the coldest temperature possible, where all motion should theoretically stop, the quantum vacuum would still buzz with an eerie, unstoppable energy. Scientists call this zero-point energy, and it's one of the most baffling secrets the vacuum keeps. Classical physics tells us that at absolute zero, everything should freeze into perfect stillness. Yet the vacuum refuses to obey. It thrums with a baseline energy that can't be removed, like a cosmic engine that never shuts off. Why does this happen? Blame it on quantum mechanics' refusal to let anything sit still. Even in their lowest possible energy state, particles jitter unpredictably, a phenomenon known as quantum fluctuations. This isn't just theoretical, we've measured it. Experiments with supercooled atoms and lasers reveal that empty space is never truly empty. There's always a faint hum of energy, as if the universe itself is vibrating at its core. Now, here's the real twist. This zero-point energy might be connected to one of the greatest mysteries in cosmology, dark energy. Astronomers know the universe is expanding faster and faster, pushed by some invisible force. The leading suspect, the energy of the vacuum itself, but there's a problem. When physicists try to calculate how much energy the quantum vacuum should have, the numbers are catastrophically wrong. They predict a universe that should have torn itself apart long ago. This glaring mismatch is called the cosmological constant problem, and it's been stumping scientists for decades. Some theories suggest we're missing a crucial piece of the puzzle, maybe exotic particles, undiscovered dimensions, or even flaws in our understanding of gravity itself. Others propose that the vacuum's energy might somehow cancel itself out in ways we don't yet grasp. Whatever the answer, one thing's clear: the quantum vacuum isn't just an oddity. It might be the hidden force shaping the entire cosmos, and if we ever crack its code, we could rewrite the story of the universe itself. So the next time you look up at the night sky, remember, what seems like vast, empty darkness is actually a seething ocean of energy, whispering clues about everything from the birth of stars to the fate of reality. And we've only just begun to listen. Picture two ultra-thin metal plates placed so close together in a vacuum that the gap between them is smaller than the width of a human hair. According to classical physics, nothing should happen, just empty space between two motionless objects. But in reality, something extraordinary occurs. The plates snap together as if pulled by an invisible hand. This is the Casimir Effect, where the quantum vacuum doesn't just whisper, it reaches out and pushes. Here's how it works. Even in a perfect vacuum, virtual particles constantly flicker into existence everywhere, filling space with a sea of temporary fluctuations. But when those two plates are brought extremely close, typically within nanometers, something changes. Only certain wavelengths of virtual particles can fit in the narrow gap between the plates, while outside, all wavelengths are free to appear. This imbalance creates a pressure difference, with more virtual particles pushing inward from the outside than from within. The result: the plates get squeezed together by what seems like pure nothingness. The implications are staggering. First observed in the laboratory in 1997, the Casimir Effect proved that quantum fluctuations aren't just mathematical quirks. They exert real, measurable forces. Today, this force from nothing isn't just a curiosity, it's a hurdle for nanotechnology. Engineers designing microelectromechanical systems, tiny moving parts in devices like smartphone sensors, have to account for Casimir attraction, which can cause components to stick together unpredictably at microscopic scales. But it's not all a nuisance. Some researchers are exploring how to harness this effect, theorizing ways to create quantum levitation by manipulating these vacuum forces. Imagine materials that repel each other without physical contact, or frictionless machinery powered by the vacuum itself. There's even speculation that advanced civilizations might one day exploit Casimir-like effects for propulsion, bending the fabric of empty space to move without expelling fuel. Perhaps most profound is what this tells us about reality. If virtual particles can create measurable forces, then the quantum vacuum isn't passive. It's dynamic, interactive, and far from empty. It suggests that what we perceive as nothing is actually a roiling quantum landscape, where even absence has structure and emptiness exerts influence. The Casimir Effect isn't just a laboratory oddity, it's a window into the hidden architecture of the universe itself, where the void is anything but vacant. What if the universe is sitting on a quantum time bomb? Not a metaphor, a literal bubble of doom that could rewrite the very laws of physics in an instant, erasing reality as we know it. This isn't the plot of a sci-fi movie. It's a genuine possibility called vacuum decay, and it starts with a simple but chilling idea. What if the vacuum of space isn't as stable as we think? Picture a ball resting at the top of a hill. It looks stable, but the slightest nudge could send it tumbling into the valley below. Now replace that ball with the entire universe, and the hill with something called the Higgs field, the invisible energy field that gives particles their mass. According to some theories, our universe might not be in the true lowest energy state, but trapped in a false vacuum, like that ball precariously balanced on the hill. If something knocks the Higgs field into a lower energy state, it could trigger a cataclysmic chain reaction. Here's how it would unfold. A tiny bubble of true vacuum would form, perhaps from a random quantum fluctuation or a high-energy particle collision. The laws of physics inside that bubble would be different. Fundamental forces might change, atoms could disintegrate, and matter itself might lose its structure. This bubble would expand at the speed of light, rewriting reality as it goes. One moment, stars, planets, and life exist. The next, everything is erased, replaced by a new universe with rules we can't even imagine. The good news, if this were possible, it probably would have happened by now. The odds of a false vacuum decay event are astronomically low, so low that scientists estimate the universe could outlast all its stars before it occurs. Yet the fact that it's even theoretically possible forces us to confront an unsettling truth. The foundations of reality might be far more fragile than they appear. Some researchers argue that if vacuum decay were imminent, we'd see evidence in the cosmos regions where physics behaves differently, like scars from previous bubble collisions. Others suggest that advanced civilizations might have ways to detect or even prevent such an event, though that's purely speculative. What's certain is that vacuum decay reminds us how little we truly understand about the quantum vacuum. It's not just empty space, it's a potential powder keg, a cosmic wild card lurking beneath the surface of existence. So while you probably don't need to lose sleep over the universe spontaneously unraveling, the mere possibility raises profound questions. Are we living in the only stable version of reality, or just one temporary arrangement in an infinite multiverse? And if the vacuum can decay, what other invisible threats might be hiding in the fabric of space itself? The answers could redefine not just our future, but our understanding of everything that came before. Take a hydrogen atom, the simplest building block of the universe, with one electron whizzing around a single proton. According to textbook physics, that electron should follow a perfectly predictable path like a planet orbiting the sun. But in the 1940s, physicist Willis Lamb noticed something odd. When he examined hydrogen's light spectrum with exquisite precision, the electron wasn't quite where it should be. Its energy levels had shifted, just a tiny bit, but enough to send shockwaves through the world of quantum theory. This minuscule discrepancy, now called the Lamb shift, became the smoking gun that proved empty space isn't placid. It's alive with invisible turmoil. What causes this quantum hiccup? Blame the vacuum's endless dance of virtual particles. Even inside an atom, the electron isn't alone. It's constantly battered by fleeting photons and particle-antiparticle pairs popping in and out of existence. These phantom interactions slightly alter the electron's path, as if it's trying to wade through a churning quantum surf. The effect is subtle, shifting energy levels by just a few millionths of an electron volt, but it's enough to warp the atom's fingerprint of light. Lamb's meticulous measurements caught this deviation, proving that even in the emptiness between an atom's nucleus and its electrons, the vacuum is tugging at the strings of reality. The discovery cracked open quantum electrodynamics, the theory governing how light and matter interact. Before Lamb, physicists struggled with infinities in their equations, mathematical nonsense suggesting particles should have infinite energy. But the Lamb shift forced them to reckon with the vacuum's role. Theorists like Richard Feynman and Julian Schwinger realized these infinities weren't flaws, they were clues. By accounting for the vacuum's ceaseless fluctuations, they could subtract its effects through a clever trick called renormalization, making predictions match reality with stunning accuracy. It was like realizing a noisy room wasn't distorting your measurements, it was part of the measurement itself. Today, the Lamb shift isn't just a historical footnote. It's etched into the precision of atomic clocks, which keep time by monitoring these very quantum jitters. It's why quantum computers must account for vacuum noise when manipulating qubits. And it hints at deeper layers. Some researchers speculate that if we could measure the shift even more precisely, we might spot anomalies pointing to undiscovered particles or forces lurking in the vacuum's shadow. So next time you hear that atoms are mostly empty space, remember, they're anything but. Every atom in your body is a storm of quantum activity, shaped by the invisible hands of the vacuum. And thanks to Willis Lamb's stubborn curiosity, we know that even the quietest corners of the universe are humming with hidden energy. Black holes are cosmic monsters, so dense that not even light can escape their grip. But what if these gravitational titans aren't as invincible as they seem? What if they're slowly leaking energy, not in spite of the quantum vacuum, but because of it? This is Hawking radiation, the shocking idea that black holes can evaporate, and it all starts with a dance between particle pairs near the event horizon. Picture the edge of a black hole where gravity is so strong that space and time twist into chaos. Here, the quantum vacuum isn't just bubbling, it's being stretched to its breaking point. Virtual particle pairs constantly flicker into existence, only to annihilate each other moments later. But near the event horizon, something bizarre happens. The black hole's gravity can wrench these pairs apart, flinging one particle into space while the other gets swallowed. The escaping particle becomes real, stealing a tiny bit of the black hole's energy in the process. Over eons, this slow trickle of stolen energy would cause the black hole to shrink and eventually vanish in a final, explosive puff of radiation. When Stephen Hawking first proposed this in 1974, it rocked physics. General relativity said black holes could only grow, devouring everything in their path. Quantum mechanics, with its unpredictable vacuum fluctuations, said otherwise. Hawking radiation became the first thread stitching these two theories together, a glimpse of how gravity and quantum weirdness might coexist, but the implications go deeper. If black holes can evaporate, where does all the information they swallowed go? Does it leak back into the universe, or is it lost forever? This information paradox still divides physicists today. Some argue that Hawking radiation carries scrambled data about what fell in, like cosmic ashes from a fire. Others believe the paradox hints at flaws in our understanding of space-time itself. And here's the wildest twist: we might actually detect Hawking radiation one day. Not from giant black holes they emit too slowly, but from tiny, artificial ones. Some labs are trying to create analog black holes using supercooled fluids or lasers, where sound or light waves mimic an event horizon. If they spot radiation leaking from these lab-made horizons, it would confirm that even the universe's darkest secrets are written in the language of the quantum vacuum. So while black holes might seem like eternal prisons, they're more like cosmic hourglasses, slowly ticking down to their own demise, and the key to their undoing. The same restless quantum emptiness that fills every inch of space. It turns out, even the universe's most terrifying beasts aren't safe from the whisper of the vacuum. You're sitting in a spaceship drifting through the vacuum of space. No stars, no planets, just pure, empty darkness. The engines ignite, and as you accelerate faster and faster, something impossible happens. The void around you suddenly feels warm, not just warm, glowing. Particles appear out of nowhere, filling your view with a ghostly heat. This isn't a hallucination. It's the Unruh effect, one of the most bizarre predictions of quantum physics, where acceleration literally rewrites reality. The effect gets its name from physicist Bill Unruh, who in 1976 realized something startling. An accelerating observer doesn't see the vacuum as empty. Instead, they perceive it as a bath of warm radiation, like standing too close to an invisible fire. Why? Because in relativity, acceleration is indistinguishable from gravity, the foundation of Einstein's equivalence principle. Just as a black hole's gravity creates Hawking radiation, your spaceship's acceleration warps the quantum vacuum into revealing particles that weren't there before. But here's where physicists start arguing. Are these particles real or just a trick of perspective? To someone floating motionless nearby, space is still a cold, empty void. Only the accelerating observer detects the heat. Some scientists argue this means the Unruh particles are illusions, mathematical artifacts with no physical substance. Others counter that since the accelerating observer could collect this radiation, measure it, even use it to power an engine, it must be as real as any other quantum phenomenon. The debate cuts to the heart of what reality even means in quantum physics. Is existence defined by what all observers agree on, or can different perspectives create their own truths? The Unruh effect suggests the latter, that the vacuum isn't just active but personal, reshaping itself depending on how you move through it. Practical detection remains elusive. For a human to feel the Unruh glow, you'd need to accelerate at a quadrillion times Earth's gravity, far beyond what any spacecraft could survive. But ingenious experiments are inching closer. Some researchers use ultra-fast lasers to mimic acceleration in quantum materials, while others probe the effect's mathematical cousins in black hole simulations. What makes the Unruh effect so haunting isn't just the science, it's the philosophical vertigo. If acceleration can conjure particles from nothing, what other realities might motion create? And if the vacuum's secrets shift with perspective, how do we ever find objective truth in a quantum universe? One thing's certain, the void isn't just watching us. It's reacting, changing its face depending on how we dare to move through it. At the smallest scales, imaginable trillions of times tinier than an atom, the smooth fabric of spacetime we know shatters into chaos. Forget the serene cosmic stage Einstein described. Here, reality resembles a churning sea of quantum foam, where space and time themselves twist, bubble, and flicker like boiling water. This isn't poetic exaggeration. It's the leading edge of physics, where the rules of gravity and quantum mechanics collide in a storm we still don't fully understand. The idea traces back to physicist John Wheeler in the 1950s. He proposed that if you could zoom in far enough, space-time wouldn't look like a flat grid. Instead, it would be a seething frenzy of tiny, wormhole-like tunnels and virtual black holes, popping in and out of existence faster than light can cross them. Imagine the universe's foundation not as solid bedrock, but as a turbulent ocean where every Planck length-sized droplet, about 10 to the power of -35 meters, is a whirlpool of possibility. Why does this matter? Because quantum foam might be the missing link between Einstein's relativity and quantum theory. Relativity paints spacetime as smooth and continuous, bending gracefully under mass and energy. Quantum mechanics, on the other hand, demands that everything, even space itself, be granular and jumpy at the tiniest scales. The foam is where these two titanic theories meet and fight. Here, gravity's orderly curves dissolve into quantum chaos, suggesting that spacetime itself might be built from something more fundamental, perhaps strings, loops, or even pixels of information. The wildest implication, quantum foam could make light itself stumble. Photons traveling across the universe might get jostled by this frothy spacetime, subtly altering their paths or energies over vast distances. Some scientists have searched for this spacetime graininess in gamma-ray bursts and distant quasars, hunting for tiny delays in high-energy light that could reveal the foam's texture. So far, no smoking gun, but the quest continues. And then there's the holographic principle, which suggests this three-dimensional foam might actually be a projection of information stored on a two-dimensional surface, like a cosmic illusion. It's as if the universe's deepest layer isn't foam at all, but a shadow play we're only beginning to decode. One thing's certain: if quantum foam is real, it means the universe isn't just built on uncertainty, it's built from it. Every moment, every location is a roiling quantum storm, hidden beneath the apparent calm of our everyday reality. And somewhere in that storm, the answers to gravity's deepest secrets might be waiting, frothing just beyond our reach. Imagine two coins flipped simultaneously on opposite sides of the galaxy. No matter how far apart they are, they always land matching heads with heads, tails with tails. Not just often, every single time. Now replace those coins with subatomic particles, and you've got the EPR paradox, one of the most mind-bending puzzles to emerge from the quantum vacuum. It's a phenomenon so strange that even Einstein called it spooky action at a distance, convinced it revealed a flaw in quantum theory. But the joke's on Einstein, because this spookiness is very, very real. Here's how it works. Take two entangled particles, say electrons, created together in the vacuum. Quantum mechanics says their properties, like spin or polarization, are linked no matter how far apart they drift. Measure one, and its twin instantly snaps into a corresponding state, even if it's light years away. No signal passes between them, no hidden wires, just an instantaneous connection that seems to shred the rulebook of classical physics, where nothing can travel faster than light. Einstein, along with physicists Podolsky and Rosen, argued in 1935 that this proved quantum theory was incomplete. They thought there must be hidden variables, secret instructions baked into the particles from birth, like cosmic cheat codes ensuring their later synchronization. But in the 1960s, physicist John Bell devised a way to test this. His theorem showed that if hidden variables existed, entangled particles would correlate only up to a certain limit. The quantum world, however, blows past that limit every time. Experiment after experiment, from photon pairs in labs to satellites beaming entangled particles across continents, confirms it. The particles really are communicating faster than light should allow. So what's really happening? One interpretation is that the particles aren't separate at all. In the quantum vacuum, distance might be an illusion, a quirk of our macroscopic perception. Entangled particles could be threads of a deeper, interconnected reality, like two ends of the same invisible string. Another wild idea is retrocausality, that measuring one particle sends influence backward in time to the moment of entanglement, collapsing both states simultaneously. The practical implications are staggering. Quantum encryption already uses entanglement to create unhackable codes. Any eavesdropper disrupts the delicate link, alerting the users. Future quantum networks might rely on this spooky action to teleport information across the globe. And some theorists speculate that space-time itself could be woven from a vast web of entangled quantum vacuum fluctuations, making entanglement not just an oddity, but the glue holding reality together. Yet the deeper mystery remains: how does the vacuum facilitate this instant connection? Is there some hidden structure, a quantum subway system, where information tunnels through the void undetected? Or does the vacuum somehow transcend space and time, operating on rules we've yet to decipher? Every answer pulls us deeper into the quantum labyrinth, where the vacuum isn't just empty space, it's the stage for the universe's most impossible magic tricks. One thing's certain: if entanglement teaches us anything, it's that the quantum vacuum plays by its own rules, and those rules are far stranger than even Einstein dared to dream. Picture an electron floating alone in space. According to classical physics, its electric field should extend outward evenly in all directions, like ripples from a pebble dropped in water. But the quantum vacuum has other plans. Surrounding that electron is a swirling crowd of virtual particle-antiparticle pairs, mostly electrons and their antimatter twins, positrons popping in and out of existence. This frenzied activity doesn't just create background noise. It fundamentally alters how the electron interacts with the world, warping its electric field in a process called vacuum polarization. Here's how it works. When a virtual electron-positron pair appears near our lone electron, something remarkable happens. The positron, drawn to the electron's negative charge, gets pulled slightly closer while the virtual electron gets pushed away. This separation creates tiny dipoles like microscopic magnets that partially shield the original electron's charge. The effect resembles how certain materials, like rubber or glass, become polarized in an electric field, earning the vacuum its surprising title, the ultimate dielectric. Quantum electrodynamics captures this with elegant Feynman diagrams, where loops of virtual particles swirl around the electron like a cosmic entourage. These loops represent the vacuum's relentless particle-antiparticle activity, and they aren't just artistic flourishes, they're mathematical blueprints explaining why the electron's effective charge grows stronger the closer you get. From afar, the polarized vacuum screens the charge, making it appear weaker, but probe at extremely short distances and the bare charge reveals itself like peeling layers off an onion. The implications ripple across physics. Vacuum polarization explains subtle shifts in atomic energy levels and fine-tunes the strength of the electromagnetic force. It's even critical for muonic atoms, exotic atoms where electrons are replaced by heavier muons whose measured energy levels initially baffled scientists until vacuum polarization corrections solved the puzzle. But the real magic lies in what this tells us about empty space. The vacuum isn't just a passive backdrop, it's an active participant, shaping forces and particles through its dynamic structure. If you could peer into the heart of an electron, you wouldn't find a solitary point of charge, but a whirlpool of quantum activity, where the very concept of empty dissolves into a sea of polarized possibilities. And somewhere in that chaos, the universe keeps its most precise ledgers, balancing what we see with what's hidden beneath. Light is supposed to be pure energy, weightless waves racing through space. But under extreme conditions, light can do something incomprehensible. It can literally transform into matter. This isn't alchemy or science fiction. It's the Schwinger effect, a phenomenon where the vacuum itself cracks open under immense electric fields, spitting out pairs of particles as if conjured from thin air. The effect takes its name from physicist Julian Schwinger, who predicted in 1951 that an electric field strong enough, approximately 10 to the power of 18 volts per meter, could tear the quantum vacuum apart. How? Think of the vacuum as a stretched rubber sheet. Normally, it snaps back when virtual particles borrow energy and vanish. But an electric field this powerful doesn't just stretch the fabric, it rips it, yanking particle-antiparticle pairs apart before they can annihilate. The energy from the field pays their debt to the universe, promoting them from fleeting virtual guests to permanent residents of reality. Nature has already tested this theory in the most extreme labs imaginable around pulsars. These rapidly spinning neutron stars generate magnetic fields so intense they warp the quantum vacuum into a particle factory. Near the star's poles, magnetic fields curve space so violently that they effectively become electric fields, triggering Schwinger pair production. Electrons and positrons flood the pulsar's magnetosphere, creating luminous jets that pulse across the cosmos like a quantum lighthouse. But here on Earth, recreating the Schwinger effect is a staggering challenge. The required field strength is millions of times beyond what our most powerful lasers can produce for now. Scientists are closing the gap with ingenious workarounds, like slamming high-energy photons together or using graphene's unique electron behavior to simulate ultra-strong fields in miniature. Recent experiments with ultra-intense lasers and crystal lattices have detected hints of vacuum breakdown. teasing the possibility of full-fledged matter from light transformation in our lifetimes. The implications are dizzying. If we could harness the Schwinger effect, we might unlock energy sources that rival stars themselves or even probe the birth of the universe when such extreme conditions were commonplace. But more fundamentally, it reveals a truth stranger than fiction. Light and matter aren't separate entities. They're two faces of the same quantum coin, flip-flopping between states in the vacuum's hidden machinery. And somewhere between the fury of a pulsar and the precision of a lab laser, we're learning to speak the vacuum's most forbidden language, the art of creation itself. Physics has a dirty little secret, a calculation so spectacularly wrong, it makes every other scientific misfire look like a rounding error. When theorists try to estimate how much energy the quantum vacuum should contain, their numbers overshoot reality by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. To put that in perspective, it's like predicting a single raindrop could flood the entire observable universe. This isn't just a minor discrepancy, it's the largest mismatch between theory and experiment in the history of science, and it's called the vacuum catastrophe. Here's where things get cosmic. Astronomers have measured the actual energy density of space, what we call dark energy, and it's tiny. So tiny, in fact, that it barely nudges the universe's expansion. Yet quantum field theory insists the vacuum should be boiling with energy, a seething foam of virtual particles packing enough punch to rip spacetime apart. How can two pillars of modern physics, quantum mechanics and cosmology, disagree so violently about something as fundamental as the energy of nothing? One unsettling possibility is that we're missing something colossal. Maybe undiscovered particles or hidden symmetries cancel out the vacuum's energy in ways we haven't imagined. Some theorists invoke supersymmetry, a hypothetical framework where every particle has a twin that could balance the scales. Others propose a bizarre form of anti-gravitational energy lurking in extra dimensions. Then there's the multiverse angle. What if our universe just won the cosmic lottery, landing in a rare bubble where vacuum energies almost but not quite cancel out? But the boldest idea, that we've misunderstood gravity itself. Einstein's theory works flawlessly at large scales, but what if it breaks down when grappling with the quantum vacuum's microscopic chaos? Modified gravity theories, like those involving massive gravitons or fractal spacetime, attempt to bridge the gap, though none yet solve the catastrophe cleanly. What makes this mystery so urgent isn't just the math. It's that dark energies whisper weak strength precisely balanced to allow galaxies, stars, and life feel suspiciously fine-tuned. As if the universe needed the vacuum's energy to be nearly, but not entirely, zero. The vacuum catastrophe isn't just physics' most embarrassing calculation. It might be pointing toward a revolution in our understanding of reality itself. And until we crack it, we're left staring into the void, wondering why emptiness refuses to add up. Imagine taking a mirror in the vacuum of space, not just any mirror, but one vibrating faster than a hummingbird's wings. Now watch as the empty space in front of it suddenly glows with real, detectable light. This isn't science fiction. It's the dynamical Casimir effect, where motion itself wrestles photons from the void, turning the quantum vacuum's hidden energy into something we can see. Here's the quantum magic at work. Remember those virtual particles flashing in and out of existence? Normally, they vanish too quickly to leave a trace. But if you vibrate a mirror at near light speeds or simulate such extreme motion in the lab, something extraordinary happens. The mirror's movement disturbs the vacuum so violently that virtual photons get kicked into reality, like ripples in a pond suddenly freezing into solid waves. The mirror's motion effectively steals energy from the vacuum's fluctuations, converting it into tangible light particles. It's as if emptiness itself is a coiled spring, and the right kind of jolt releases its pent-up energy. In 2011, physicists at Chalmers University of Technology pulled off this feat with a clever workaround. Instead of physically moving a mirror at impossible speeds, they used a superconducting quantum interference device, or SQUID, to mimic a mirror's oscillation by flipping a magnetic field trillions of times per second. The result, microwave photons emerging from what should have been pure nothingness, marking the first experimental confirmation of the dynamical Casimir effect. The implications stretch far beyond a lab curiosity. For quantum thermodynamics, this effect blurs the line between heat and light. Some researchers theorize that ultra-fast, moving boundaries could one day engineer vacuum fluctuations into a new kind of energy source, or even cool quantum systems by siphoning thermal noise back into the vacuum. Others speculate that advanced civilizations might exploit similar principles to harvest energy from spacetime itself. But the most profound lesson lies in what this tells us about reality. The vacuum isn't just a static backdrop, it's a dynamic medium rich with untapped energy waiting for the right trigger. And if shaking a mirror can summon light from darkness, what other secrets might the quantum vacuum yield when we learn to move in just the right way? The dynamical Casimir effect doesn't just illuminate photons, it illuminates how deeply motion and emptiness are entwined in the fabric of the universe. In the late 1920s, physicist Paul Dirac stared at an equation that seemed to predict something impossible: electrons with negative energy. To him, this wasn't just a mathematical quirk, it was a cosmic clue. He proposed a radical vision: the vacuum isn't empty. It's an infinite churning ocean of electrons packed so tightly that they fill every possible energy state below a certain threshold. This was the Dirac Sea, a universe where what we call nothing is actually a submerged plenum brimming with invisible particles. Here's where it gets wild. Dirac realized that if an electron in this sea were somehow lifted out, it would leave behind a hole, a sort of bubble in the quantum foam, and that hole wouldn't just sit there. It would behave exactly like a particle with the same mass as an electron, but the opposite charge. In other words, a positron, the antimatter twin of the electron. At the time, antimatter was purely theoretical, but just 4 years later, cosmic ray experiments detected positrons, proving Dirac's ocean wasn't just poetic imagery, it had predictive power. Yet today, we don't talk about the vacuum as a literal electron sea. Quantum field theory, the modern framework, replaced Dirac's metaphor with something even stranger: a void teeming with potential, where particles are excitations of invisible fields, like vibrations on a cosmic guitar string. So why abandon the Dirac Sea? 2 reasons. First, the math got messy when applied to particles like photons, which don't have antiparticles in the same way. Second, the sea implied an infinite negative energy density, a troubling idea when general relativity insists that energy warps spacetime. But here's the twist: the Dirac Sea never truly left us. Its mathematics still underpin quantum electrodynamics. Those holes became the positrons in Feynman diagrams, and the sea's structure morphed into the concept of the Fermi sea in condensed matter physics, where electrons in materials behave like a miniature Dirac ocean. Even Hawking radiation borrows from Dirac's playbook. The black hole's event horizon acts like a cosmic shoreline, dredging particle pairs from the vacuum's depths. The real lesson: sometimes the wrong idea points to the right answer. Dirac's Sea was a stepping stone, a flawed but brilliant metaphor that helped us navigate toward a deeper truth. The vacuum isn't water, but it's not nothing either. It's a dynamic medium where every empty point hides infinite potential, waiting for the right equation or the right experiment to reveal its next secret. Imagine pouring a cup of water into a bowl, only to watch it climb up the sides and spill over without any friction, not a single drop left behind. This isn't a magic trick. It's the behavior of a superfluid, a state of matter where atoms move in perfect unison, utterly indifferent to the usual rules of viscosity. Now take that idea and stretch it across the universe. What if space-time itself, the very fabric of reality, flows like a cosmic superfluid at the smallest scales? Welcome to one of the most tantalizing whispers from the quantum vacuum, the possibility that emptiness isn't just active but slippery. The idea emerges from an unlikely marriage of disciplines. In condensed matter labs, superfluids like helium-4 defy gravity, creep through impossibly thin cracks, and even form quantum whirlpools that never dissipate. These quirks arise because the fluid's atoms lock into a single quantum state, moving as one coherent wave rather than individual particles. Now, theorists like Stefano Liberotti and others have asked, could the vacuum's underlying structure behave similarly? If space-time has a granular quantum nature, like a fluid made of indivisible atoms of space and time, then it might flow without resistance when probed at tiny enough scales. Analog gravity experiments add fuel to this speculative fire. By simulating black holes in superfluid helium or Bose-Einstein condensates, physicists have spotted eerie parallels between how sound waves move in these fluids and how light bends near cosmic singularities. In some setups, ripples in the superfluid mimic Hawking radiation so precisely that it hints at a deeper connection. Perhaps space-time itself flows like an exotic quantum fluid, with black holes acting as cosmic drains. Critics argue that drawing this analogy too literally risks poetic overreach. After all, space-time isn't made of atoms, and the Planck scale, where these effects might surface, is 18 orders of magnitude smaller than anything we've measured. But supporters counter that the math doesn't lie. Certain quantum gravity models, like loop quantum cosmology, predict space-time could exhibit superfluid-like properties near the Big Bang or inside black holes where densities reach extreme levels. The implications would rewrite physics. A superfluid vacuum could explain why the universe's expansion appears so smooth, as if space-time slides without internal friction. It might offer new clues about dark energy, or even suggest that empty space can undergo phase transitions, freezing, melting, or cracking under the right conditions. And if space-time flows, could we someday manipulate its viscosity? The wildest speculations imagine technologies that steer this superfluid, though for now that remains firmly in the realm of theory. Whether or not the vacuum truly is a superfluid, the metaphor alone has already proven its worth. It challenges us to rethink nothingness not as static emptiness, but as a dynamic medium with properties we're only beginning to glimpse. And somewhere between the chill of a lab's helium bath and the seething foam of quantum gravity, we might just find the universe's slickest secret, that even space-time knows how to go with the flow. What if everything you see, the stars, your hands, even the empty space between them, is just a projection, like a movie playing on the surface of an invisible screen? This isn't a metaphor, it's the holographic principle, one of the most radical ideas in modern physics, suggesting the quantum vacuum might not be three-dimensional at all. Instead, it could be a two-dimensional illusion, a cosmic trick where every bit of information about our universe is secretly encoded on a distant boundary, like data etched onto the surface of a DVD. The idea first took root in the study of black holes. In the 1970s, physicist Jacob Bekenstein calculated that a black hole's entropy, a measure of its hidden information, is proportional not to its volume but to the area of its event horizon. This was baffling. In everyday systems, entropy grows with volume, but black holes seem to obey different rules, as if their inner workings were painted onto their surfaces. Years later, string theorists like Leonard Susskind and Gerard T. Hooft ran with this clue, proposing that the entire universe might work the same way. Just as a hologram encodes a 3D image on a 2D film, the vacuum could be storing all the information about particles, forces, and even space-time itself on some far-flung boundary we can't see. Think of it like this. Imagine watching a video game where every character, tree, and explosion is rendered in stunning detail. but under the hood, all that complexity boils down to lines of code on a flat, two-dimensional chip. The holographic principle suggests reality operates similarly. The quantum vacuum's ceaseless activity, virtual particles, entangled states, even the fabric of spacetime, might just be the graphics generated by deeper, simpler rules written on the universe's edge. Evidence is tantalizing but indirect. Certain models of quantum gravity, like string theory in anti-de Sitter space, mathematically support the idea. In these frameworks, calculations that seem impossible in 3D become tractable when shifted to a 2D boundary, as if the universe is doing its accounting on a cosmic spreadsheet. Even the AD/S/CFT correspondence, a theoretical bridge between gravity in higher dimensions and quantum fields in lower ones, hints that the vacuum's true nature might be flatter than we think. But if the vacuum is a hologram, where's the projector? Some theorists speculate the boundary could lie at the infinite edge of the cosmos, or even inside every piece of space like a fractal pattern. Others suggest it's not a literal screen, but a mathematical duality, a way of describing reality that's equivalent to living on a surface, even if we can't point to it. The implications are staggering. If the holographic principle is right, it means the vacuum's apparent depth, the very thing that makes space feel vast and three-dimensional, is an elaborate illusion. Black holes aren't just storing their secrets on their surfaces. Everything might be. From the spin of an electron to the expansion of galaxies, all of it could be pixels in a cosmic projection, with the quantum vacuum as the flickering screen. This isn't just about rewriting physics textbooks, it's about redefining what real even means. If the vacuum is a hologram, then the universe isn't just stranger than we imagine, it's stranger than we can imagine. And somewhere between the math and the mystery, we might finally uncover the ultimate cheat code, the one that reveals who or what is holding the projector. Dark matter is the universe's most persistent ghost. We know it's there. Its gravity holds galaxies together, bends light, and sculpts the cosmic web. But after decades of searching, we still haven't caught a single glimpse of it directly. What if we've been looking in the wrong places? What if dark matter isn't hiding in the shadows of space, but in the quantum vacuum itself, woven into the fabric of emptiness? The idea isn't as far-fetched as it sounds. Take actions, hypothetical particles so light and shy they barely interact with ordinary matter. Theorized in the late 1970s to solve a puzzle in particle physics, these elusive candidates could be born from the vacuum's own fluctuations. Picture the vacuum as a cosmic piano, with actions as notes so faint they're drowned out by the universe's noise until now. Recent experiments like ADMX and Koltask are tuning into this quiet frequency, using ultra-sensitive magnetic fields to coax actions out of hiding. If they exist, they'd behave less like traditional particles and more like waves rippling through the vacuum's hidden depths, but actions are just the beginning. Some theories propose entire, hidden sectors of particles that only talk to our world through the vacuum's subtle intermediaries. Imagine two groups of people separated by a thick curtain, whispering through the fabric. In this analogy, the curtain is the quantum vacuum, and the whispers are rare, weak interactions mediated by vacuum fields. These hidden particles could account for dark matter's invisibility, not because they're rare, but because they're entangled with the vacuum in ways we're only starting to map. The most radical possibility, dark matter might not be made of particles at all. Instead, it could be a property of the vacuum itself, a sort of quantum texture or defect frozen into spacetime during the universe's fiery birth. Think of it like cracks in ice, invisible until you tilt the surface just right. Certain theories, like topological defects or solitons, suggest dark matter could be knots in the vacuum structure, gravitational fossils from when the cosmos first cooled. If true, we wouldn't detect dark matter by catching particles, but by sensing its gravitational imprint on the vacuum's hidden geometry. Why does this matter? Because if dark matter is tied to the vacuum, it changes how we hunt for it. Instead of building bigger detectors to spot rare collisions, we might need to listen for the vacuum's quiet hum, searching for anomalies in fields and forces we once thought were empty. It's like realizing the ghost in your house wasn't hiding in the walls, it was the walls. The quantum vacuum has already appended our ideas of nothingness. Now it might hold the key to the universe's greatest missing piece. And if we're right, the darkest stuff in existence could be hiding in plain sight, woven into the void itself. What if simply looking at the universe could change how it behaves, not metaphorically, literally? Imagine a radioactive atom that refuses to decay, frozen in time, simply because you keep checking on it too often. This bizarre phenomenon is called the quantum Zeno effect, where the act of observation doesn't just disturb reality, it locks it in place, like hitting pause on a cosmic remote control. Here's how it works. In the quantum vacuum, particles exist in superpositions, ghostly states of maybe, where an electron can spin both up and down until measured. But every time you peak, the system collapses into a definite state. Now imagine peaking continuously, bombarding a particle with observations before it has time to evolve. The math shows something astonishing. The more you measure, the slower it changes, like a deer caught in headlights. Eventually, with enough scrutiny, the system freezes entirely, trapped in its initial state by the sheer weight of your gaze. The name comes from an ancient Greek paradox, Zeno's arrow, which argues that if you slice time into infinitesimal moments, motion becomes impossible. Quantum mechanics takes this idea and runs with it. In labs, physicists have seen this play out with qubits, the building blocks of quantum computers. Leave a qubit alone and it'll eventually flip states, but monitor it incessantly and it'll stubbornly stay put, as if the universe is too shy to change under scrutiny. This leads to one of quantum theory's most haunting questions. Is the moon there when nobody looks? If observation shapes reality at the atomic scale, could it apply to larger objects? Most physicists say no. The Zeno effect gets drowned out by environmental noise in big systems, but the deeper philosophical itch remains. If a tree falls in a quantum forest with no one to measure it, does it make a sound? Or does it hover in a fog of possibilities until observed? The implications stretch far beyond thought experiments. In quantum computing, the Zeno effect is both a weapon and a weakness. Harness it, and you could protect qubits from errors by freezing them mid-calculation. Ignore it, and your overeager measurements might sabotage the very computation you're trying to run. Even biology isn't immune. Some theories suggest enzymes might exploit Zeno-like effects to stabilize reactions, blurring the line between quantum and life. But here's the twist. The Zeno effect has an evil twin. The anti-Zeno effect, where frequent observations accelerate decay instead of preventing it. It's as if the universe, tired of being watched, decides to rush through its changes just to spite you. Which one wins depends on timing, energy gaps, and the fine print of quantum theory. A reminder that the vacuum doesn't play by human rules. So next time you check your phone for notifications, remember, at some level, reality itself might be holding its breath, waiting to see if you'll look away long enough for the magic to happen. And in that fragile gap between glances, the quantum vacuum dances. In a lab in Germany, scientists have created a black hole. Not the kind that devours stars, but a tiny, controlled echo of one, conjured from a cloud of atoms chilled to near absolute zero. This is the magic of Bose-Einstein condensates, where rubidium or sodium atoms slow down so much that they merge into a single quantum wave, behaving less like individual particles and more like a miniature universe. And inside this frigid playground, physicists are bending the rules of reality to simulate the quantum vacuum's wildest phenomena. Take the experiment by Jeff Steinhauer at the Technion in Israel, where a sonic black hole was engineered in a Bose-Einstein condensate. By manipulating the condensate's flow, his team created a point where sound waves like light near a real black hole couldn't escape. The result, Hawking radiation, the very same particle emission predicted to leak from cosmic black holes, appeared in the lab as faint ripples in the atomic soup. It was as if the vacuum's hidden mechanics had been distilled into a tabletop experiment, proving that the void's secrets can be teased out with ultra-cold atoms and lasers. But black holes aren't the only cosmic mysteries being reborn in these labs. Some teams are simulating the infant universe itself. Just after the Big Bang, space is thought to have expanded exponentially in a process called inflation, a burst of growth so rapid it left ripples in space-time. In a lab at the University of Cambridge, researchers replicated this by suddenly stretching a Bose-Einstein condensate, watching as quantum fluctuations morphed into patterns eerily similar to the primordial seeds that later became galaxies. The vacuum's randomness, it seems, isn't just noise, it's the universe's way of rolling the dice on structure. Why does this matter? Because these experiments aren't just imitations, they're windows. When you can't travel to a black hole or rewind time to the Big Bang, you rebuild them. The quantum vacuum's rules appear universal, playing out whether you're probing the edge of a singularity or a cloud of atoms in a magnetic trap. And with every lab-grown black hole or simulated cosmic dawn, we're learning that emptiness isn't passive, it's a dynamic stage where the same scripts repeat across scales. The real breakthrough isn't just the science, it's the perspective. These experiments suggest that the quantum vacuum might be less like a featureless void and more like a programmable medium, where the right conditions can boot up snippets of space-time itself. Who knows, maybe one day we'll engineer entire pocket universes in the lab, testing ideas about dark energy or extra dimensions not with telescopes but with lasers and atoms. For now, every ultra-cold simulation is a whisper from the vacuum, reminding us that the universe's grandest mysteries might be hiding in the smallest, coldest corners of our own labs. What if radiation emitted by an atom today was secretly guided by events that haven't happened yet? This isn't time travel, it's the Wheeler-Feynman absorber theory, a radical proposal that rewires our understanding of cause and effect by suggesting the quantum vacuum isn't just chaotic, it's clairvoyant. The idea began in the 1940s when physicists John Wheeler and Richard Feynman tackled a puzzling question. Why does an accelerating electron radiate energy in some directions but not others? Classical electrodynamics had equations but no satisfying story. Their solution flipped the script entirely. They proposed that radiation isn't just emitted into the vacuum, it's a two-way handshake between the electron and every charged particle in the universe, past and future. Here's how it breaks down. When an electron accelerates, it sends out electromagnetic waves rippling forward in time, the usual radio waves or light we'd expect. But Wheeler and Feynman argued these waves are only half the picture. The vacuum, they claimed, also carries advanced waves, signals that travel backward in time from every particle that will ever absorb the radiation. These time-reversed waves converge on the original electron, guiding its radiation pattern like an invisible choreographer. The result, the electron only emits energy where the universe's future absorbers tell it to. This sounds like mystical nonsense until you run the math. Astonishingly, the equations balance perfectly. The sum of ordinary forward time and advanced backward time waves cancels out everywhere except where absorption actually occurs, neatly explaining why radiation appears directional. It's as if the vacuum serves as a cosmic ledger, keeping accounts between emitters and absorbers across time itself. The implications ripple into modern quantum weirdness. The absorber theory resurfaced in debates about retrocausality, the idea that future events can influence the past. In quantum experiments like the delayed choice setups, particles seem to decide their behavior based on measurements made after they've already traveled. Wheeler-Feynman's time-symmetric waves offer a tantalizing framework. perhaps the vacuum doesn't just mediate these connections, it enforces them, weaving causality into a loop where past and future negotiate reality's terms. Critics dismiss the theory as a clever trick with no experimental proof, but supporters point to eerie echoes in quantum optics, where certain light-matter interactions behave as if future conditions constrain present emissions. And in the murky realm of quantum foundations, where time's arrow remains a mystery, the Wheeler-Feynman model stands as a bold reminder. The vacuum might not just remember the past, it could be taking notes from the future. So next time you turn on a radio, consider this. The static between stations isn't just noise. It's the sound of the universe balancing its books, with the quantum vacuum acting as both scribe and oracle. A place where radiation doesn't just go out into the void, but where the void whispers back through time itself. Picture a material so finely crafted that it doesn't just bend light, it bends emptiness itself. These are vacuum metamaterials, nanostructured designs so precise they can sculpt the quantum vacuum's fluctuations like clay, turning science fiction into laboratory reality. At their core, they exploit a simple but radical idea. If the vacuum is a seething ocean of virtual particles, why not build tiny anchors to steer its waves? The magic happens at scales smaller than a wavelength of light. By arranging nanoscale pillars, wires, or cavities in precise patterns, engineers create surfaces that interact with virtual photons in ways ordinary matter never could. One application: invisibility cloaks that don't just redirect light, but suppress the vacuum's natural emissions around an object, rendering it undetectable to certain sensors. Imagine a submarine that doesn't just avoid sonar, it silences the quantum whispers that might give it away. But invisibility is just the start. Some metamaterials act as perfect lenses, using vacuum fluctuations to focus light beyond the diffraction limit, a barrier long thought unbreakable. Normally, light blurs when squeezed too tightly, like trying to write with a melted crayon. Yet certain metamaterials, like those made of silver nanowires or hyperbolic stacks, amplify evanescent waves, ghostly light that typically dies out instantly. By harnessing the vacuum's energy, these lenses resurrect those vanishing waves, revealing details smaller than the light's own wavelength. It's like using a magnifying glass to see the individual atoms in a grain of sand. The real breakthrough lies in the underlying physics. These materials don't just passively respond to light, they reprogram the local quantum vacuum. Picture a crowded dance floor where everyone moves chaotically until you lay down tiles that force dancers into specific steps. Metamaterials do the same for virtual particles, creating zones where the vacuum's randomness is tamed into useful order. In some lab setups, this has led to negative refraction, where light bends backward, or trapped rainbow effects, where different colors stop dead in their tracks. Yet the wildest possibilities remain theoretical. Hypothetical space-time cloaks could exploit metamaterials to bend not just light but time, creating pockets where events leave no trace. Others envision quantum levitation platforms that repulse objects by manipulating vacuum forces, or noise-free quantum computers shielded by metamaterial cocoons that filter out disruptive fluctuations. Of course, challenges abound. Many vacuum metamaterials only work at specific frequencies or require impossibly cold temperatures. But with every nanofabrication advance, we inch closer to materials that don't just exist in space, but rewrite the rules of emptiness around them. The quantum vacuum isn't just a backdrop anymore, it's a construction site, and the architects are learning to build with nothing. Could your thoughts, your very consciousness, be intertwined with the quantum vacuum? It's a question that blurs the line between neuroscience and quantum physics, sparking debates so heated they've divided scientists for decades. At the heart of this controversy is the Penrose-Hameroff theory, a bold proposition that suggests our brains might exploit quantum processes happening in the very fabric of spacetime. Roger Penrose, a Nobel-winning physicist, and Stuart Hameroff, an anesthesiologist, argue that consciousness isn't just the result of neurons firing, it's a quantum phenomenon. Their theory, dubbed orchestrated objective reduction, posits that tiny structures inside neurons called microtubules act as quantum computers, processing information through vibrations in the quantum vacuum. These vibrations collapse into conscious moments like notes in a cosmic symphony. It's a poetic idea that the vacuum's fluctuations might be the hidden conductor of our inner experience. But here's where the skepticism kicks in. Critics point out that the warm, wet environment of the brain is a far cry from the ultra-cold, isolated conditions needed for quantum coherence in labs. Quantum states are notoriously fragile, decohering at the slightest disturbance. How could they survive the chemical chaos of a living brain? Yet Penrose and Hameroff counter with recent research showing evidence of quantum vibrations in microtubules even at biological temperatures. Some studies even suggest anesthetic gases which selectively switch off consciousness might work by disrupting these quantum processes. The debate spills into philosophy. If consciousness is rooted in the quantum vacuum, does that mean the universe itself has a proto-consciousness? Panpsychists argue yes, that experience might be a fundamental feature of reality, like mass or charge. Others dismiss this as speculative overreach, insisting that consciousness emerges from classical neuron networks, not quantum magic. What makes this more than just a fringe idea is the deeper question it raises. Could the vacuum be more than a backdrop? Could it actively participate in the phenomena we call mind? For now, the theory remains provocative but unproven, a reminder that the quantum vacuum's mysteries might not just lie in the stars, but inside our own skulls. And whether Penrose and Hameroff are right or wrong, their audacious hypothesis forces us to ask, if the vacuum can birth particles and shape space-time, why not thought itself? Absolute zero, the coldest temperature possible, where all molecular motion supposedly stops, has long been considered the ultimate chill. But the quantum vacuum doesn't play by those rules. Even in the deepest void of space, where thermometers would theoretically bottom out, there's a faint, stubborn warmth that refuses to disappear. Not from distant stars or cosmic background radiation, but from the vacuum itself, a whisper of heat woven into the fabric of nothingness. This isn't just theoretical hand-waving. The Unruh Effect tells us that an accelerating observer sees the vacuum glow with heat, while Hawking radiation proves black holes emit warmth from their event horizons. Both phenomena suggest something radical. Empty space has a temperature, even if it's vanishingly small. For a spaceship accelerating at a quadrillion times Earth's gravity, that glow would feel like a warm breeze. For a hypothetical thermometer placed near a black hole, it would register a faint but measurable warmth. But here's the kicker, these effects aren't just localized quirks. They hint that the vacuum itself might carry a baseline thermal energy, a relic of its ceaseless quantum activity. What does this mean for quantum computers, the ultra-sensitive machines that harness quantum states to perform calculations? These devices operate at temperatures just a hair above absolute zero to minimize thermal noise, the random jostling of atoms that can destroy fragile quantum information. But if the vacuum itself emits heat, even in tiny amounts, it could pose a fundamental limit to how stable qubits can ever be. Imagine building a sandcastle too close to the tide. No matter how carefully you sculpt it, the ocean's edge will eventually creep in. Similarly, vacuum fluctuations could be the ultimate noise floor, a cosmic whisper that even the most advanced refrigeration can't silence. Some researchers are already probing this boundary. In labs studying superconducting qubits, unexplained energy shifts sometimes appear, tiny blips that could be signatures of vacuum thermal effects. Other teams are designing experiments to isolate and measure these residual energies, hoping to distinguish between classical thermal noise and true quantum vacuum contributions. The stakes are high. If the vacuum's warmth is unavoidable, engineers might need entirely new approaches to error correction, or even rethink the materials used to build quantum processors. But there's a tantalizing flip side. If we can understand this vacuum heat, we might learn to exploit it. Just as black holes turn vacuum energy into Hawking radiation, future quantum devices could potentially harvest or redirect these fluctuations, turning noise into a resource. Picture a quantum computer that doesn't just tolerate the vacuum's whispers, but dances with them, using their rhythm to stabilize calculations instead of disrupting them. The unsettling truth, absolute zero, might be a myth, not because our refrigerators aren't good enough, but because the universe itself refuses to sit still. Even in the deepest void, the quantum vacuum hums with energy, a reminder that true nothingness doesn't exist. And as we push the limits of quantum technology, we're not just fighting engineering challenges, we're wrestling with the universe's coldest, quietest secret. What if the quantum vacuum isn't just a chaotic sea of particles, but a cosmic tunnel builder? Imagine a shortcut through space-time, a wormhole linking two distant points in the universe, held open not by exotic matter or brute force, but by the vacuum's own restless energy. This isn't just science fiction. It's a tantalizing possibility emerging from the wildest edges of theoretical physics, where the vacuum's fluctuations might not just fill space, they could reshape it. The idea hinges on a radical proposal called ER equals EPR, born from the minds of string theorists Juan Maldacena and Leonard Susskind. They suggested that wormholes, Einstein-Rosen bridges, or ER for short, might be intimately connected to quantum entanglement, dubbed EPR after Einstein, Podolsky, and Rosen. In this framework, two entangled particles could be linked by a microscopic wormhole, a tiny tunnel through space-time forged by the vacuum's quantum glue. It's as if every spooky action at a distance isn't just a weird connection, it's a physical bridge hidden in the fabric of nothingness. But here's the twist: wormholes are notoriously unstable. According to general relativity, they'd snap shut faster than light can traverse them unless propped open by negative energy, something repelling gravity itself. This is where the quantum vacuum could step in. Virtual particles constantly borrowing energy from the void don't just flicker randomly, they create fluctuations in energy density, some of which could theoretically exhibit negative pressure. If harnessed, these fluctuations might stabilize a wormhole's throat, like microscopic hands gripping the sides of a collapsing tunnel. Science fiction loves this idea. From Interstellar's Gargantua to Star Trek's subspace networks, wormholes are the ultimate plot device for cosmic travel, but the reality could be stranger. If ER equals EPR holds, the quantum vacuum might be threaded with countless microscopic wormholes, each tying together entangled particles across the universe. These wouldn't be the grand celestial highways of sci-fi, they'd be vanishingly small, fleeting structures, more like quantum threads stitching space-time together from the inside. Yet the implications are colossal. If vacuum-stabilized wormholes exist even at microscopic scales, they could redefine our understanding of connectivity in the universe. Information might not need to travel across space, it could slip through it, bypassing light speed limits via the vacuum's hidden plumbing. Some theorists even speculate that black holes, those cosmic vacuum cleaners, might secretly be wormhole endpoints, their interiors connected to distant regions of spacetime through quantum entanglement. Of course, the hurdles are astronomical. No one knows how to scale up these hypothetical wormholes, or whether vacuum fluctuations could ever provide enough negative energy to keep them open. The math is speculative, the energy requirement staggering, but the mere possibility forces us to confront a profound question. Is the quantum vacuum just the stage, or is it also the architect quietly engineering shortcuts through the cosmos? Whether or not we ever traverse these tunnels, their potential existence reminds us that emptiness isn't passive. It's a dynamic, creative force, endlessly rewriting the rules of reality behind the scenes. And if the vacuum can birth particles and bend spacetime, who's to say it can't also stitch the universe together, one wormhole at a time? Imagine zooming in on the fabric of spacetime closer, until the smooth continuum dissolves into a shimmering web of tiny, indivisible loops. This isn't science fiction. It's the heart of loop quantum gravity, a radical theory that suggests spacetime isn't a blank stage but a dynamic tapestry woven from threads of the quantum vacuum itself. Forget empty space here. Reality is built from interlocking atoms of gravity, each a billion trillion times smaller than an atom, vibrating with primordial energy. At this scale, the vacuum isn't just active, it's structural. Picture spacetime as a mesh of interconnected rings like chainmail armor for the universe. These loops don't exist in space, they are space, defining distance and time through their interactions. When matter moves, it's not sliding across an empty grid, it's tugging on this cosmic net, stretching and twisting the vacuum's very fabric. It's a vision worlds apart from string theory, where spacetime is a backdrop for dancing strings. Here, the vacuum is the dance. The math behind this is dizzying. Loop quantum gravity quantizes spacetime itself, meaning you can't divide it infinitely. There's a smallest possible patch, a Planck-sized pixel of reality. Black holes reveal this starkly. According to loop theory, matter crushed into a singularity doesn't vanish into infinity, but hits a wall where space loops back on itself, like a Möbius strip turned inside out. Some models even suggest black holes could birth new universes this way, with the vacuum's loops knitting fresh spacetime from the wreckage. String theory, by contrast, treats spacetime as a fixed arena where strings vibrate in extra dimensions. The vacuum is more like a resonating medium, a multidimensional stage where strings perform. But loop quantum gravity flips the script. No extra dimensions, no fundamental strings. Just the vacuum's loops braiding and unbraiding to create particles, forces, and even time's arrow. Which approach is right? The debate rages. String theory excels at unifying forces but struggles to pin down spacetime's quantum nature. Loop quantum gravity tackles spacetime head-on but hasn't yet woven all forces into its fabric. Yet both share a profound insight. The quantum vacuum isn't just the universe's static foundation. It's the living, breathing loom where reality is stitched together, one loop or one string at a time. The real magic lies in what this means for nothingness. Whether loops or strings win, the message is clear. The vacuum isn't passive. It's the universe's most skilled artisan, crafting spacetime itself from raw quantum potential. And somewhere in those threads, the answers to gravity's deepest secrets might be waiting tangled, but not out of reach. What if our universe is just one bubble in an endless cosmic foam, a single reality adrift in a sea of others? This isn't just speculation. It's a startling possibility emerging from the quantum vacuum's most volatile behavior, vacuum decay. But the story doesn't end with our universe unraveling. It might begin with an infinity of others already doing so, colliding, merging, and birthing new cosmic realms in a process called eternal inflation. Picture the vacuum not as a static void, but as a pot of water heated past boiling. Most of it is a roiling chaos, but here and there, bubbles form regions where the quantum fields suddenly settle into a lower energy state. Each of these bubbles is a new universe with its own laws of physics expanding at unimaginable speeds. Our universe could be one such bubble, a pocket of stability in a storm of quantum chaos. And just like bubbles in a fizzy drink, these cosmic realms might occasionally bump into each other, leaving scars we could detect. The math behind this is both elegant and unsettling. Eternal inflation suggests that the vacuum's high energy state drives exponential expansion, but random quantum fluctuations create pockets where that energy drops, forming bubble universes. Some of these bubbles might have stronger nuclear forces, making stars burn differently. Others could have extra dimensions or reversed arrows of time. The diversity is limitless, all sprouting from the same quantum substrate. But how would we know? The answer lies in the cosmic microwave background, the afterglow of the Big Bang. If our bubble universe ever collided with another, the impact would send shockwaves through space-time, leaving faint, circular imprints in this ancient light. Teams like those analyzing Planck satellite data have scoured the sky for these patterns, hunting for concentric rings of temperature variation that could betray a long-ago cosmic fender bender. So far, no definitive proof, but the search continues. Even wilder are the simulations. Supercomputers modeling bubble collisions show intricate fractal boundaries like soap suds merging in slow motion. These virtual universes reveal that collisions wouldn't be rare, just hard to spot, like finding a single fingerprint on a planet-sized balloon. Some models even suggest that bubble universes could bud off each other, creating a branching multiverse where realities spawn new realities in an endless cascade. The implications rewrite existence itself. If eternal inflation is real, the quantum vacuum isn't just the engine of our universe. It's a factory for all possible universes, each a separate experiment in physics. And somewhere in that froth of realities, the vacuum might be brewing another bubble right now, one that could rewrite the rules of reality all over again. The question isn't just whether we're alone in this universe, it's whether we're alone in the vacuum's unimaginable sprawl. Silence isn't silent. Even in the deepest void of space, where no star shines and no cosmic wind blows, there's a sound, a whisper of quantum static humming beneath the fabric of reality. It's not a sound you can hear with your ears, but one that echoes through the most sensitive machines humanity has ever built. Gravitational wave detectors like LIGO. These colossal instruments, designed to catch ripples in space-time from colliding black holes, are locked in an endless battle against a far subtler foe, the quantum vacuum's relentless noise. Picture LIGO laser beams racing down 4-kilometer-long tunnels, bouncing between mirrors so precisely suspended that they're virtually free from Earth's tremors. The goal, to detect changes in mirror positions smaller than a 10,000th the width of a proton. But here's the catch, the quantum vacuum won't let those mirrors sit still. Virtual particles constantly pop into existence around them, jostling the mirrors with random, infinitesimal kicks. It's like trying to measure the flutter of a butterfly's wings while standing in a hurricane. This isn't just background static. It's a fundamental limit, a murmur from the vacuum itself reminding us that perfect stillness doesn't exist. To grasp how weird this gets, imagine the vacuum's noise as a cosmic orchestra where every instrument is playing at once, but no two notes align. Photons, gravitons, even ghostly particles we haven't named yet, all contribute to a dissonant hum that physicists call quantum fluctuation noise. LIGO engineers don't just fight this noise, they've learned to dance with it. By squeezing light, a quantum trick that trades precision in one property for certainty in another, they can partly mute the vacuum's chatter, like turning down the volume on a radio static without losing the song beneath. But the vacuum isn't just an obstacle. Its noise might hold clues to deeper physics. Some theorists suggest that if we listen closely enough, subtle anomalies in this quantum static could reveal hidden particles or extra dimensions. Others propose that the vacuum's hum could one day be harnessed, like capturing the random energy of ocean waves to power a city. For now, though, the sound remains a paradox, a reminder that the universe's quietest corners are anything but empty. Every time LIGO hears a gravitational wave, it's not just detecting the distant crash of black holes. It's eavesdropping on a conversation between the cosmos and the quantum void, where even silence has something to say. Time might feel like the most familiar part of existence, the steady tick of a clock, the unstoppable march from past to future. But what if time isn't fundamental at all? What if it's just an illusion, a side effect of something far stranger happening in the quantum vacuum? This isn't just philosophical musing, it's a radical idea gaining traction in physics. That time emerges from the vacuum's tangled web of quantum entanglement, like a movie projected from the static of a broken television. Start with the puzzle of entropy, the universe's natural tendency toward disorder. We think of time as flowing because entropy always increases, like an egg cracking but never uncracking. But at the quantum level, this arrow of time might trace back to the vacuum's entanglement, entropy, a measure of how tangled particles are across space. Every time two particles interact, they leave behind entanglement, threads in the vacuum, weaving a complex network. Some theorists believe it's this growing web of connections that creates the illusion of time passing, like a cosmic knitting project where each stitch is another moment. The evidence comes from quantum clocks, devices so precise they can measure time by watching how entangled particles evolve. In experiments at the University of Oxford, researchers used pairs of entangled ions as microscopic timekeepers. When left alone, their entangled states evolved predictably, marking time like quantum metronomes. But when researchers selectively cut entanglement threads between the ions, something bizarre happened. The clocks lost sync, as if time itself stuttered. It was as though entanglement wasn't just measuring time, it was creating it. This gets even weirder when applied to black holes. According to quantum gravity, the event horizon's entanglement entropy, the chaos of virtual particles at the boundary, might encode time's flow for the entire universe. Imagine spacetime as a hologram, with the vacuum's entanglement patterns projecting time like a flickering shadow on the cave wall. The more tangled the vacuum, the more time emerges. But here's the twist. If time is just entanglement entropy, what happens at the Big Bang or deep inside a black hole where quantum gravity reigns supreme? Some models suggest time could freeze or shatter into fragments, like a broken clock spinning randomly. Others propose that multiple timelines could branch from a single vacuum state, each a different knot in the quantum web. The most mind-bending implication: if time is emergent, not fundamental, then the past, present, and future might all exist at once. A frozen block universe where change is just an artifact of how entangled we are with the vacuum's hidden layers. It's a vision where time isn't a river flowing, but a tapestry being woven, thread by quantum thread. And every observation we make, every tick of the clock, is just another tug on the vacuum's strings. What if the fabric of reality isn't smooth or even grainy, but infinitely crinkled, like a piece of paper folded over and over until it becomes a labyrinth of jagged edges? This is the mind-bending idea behind fractal spacetime, where the quantum vacuum doesn't just foam at the smallest scales. It spirals into endless complexity, a cosmic echo of patterns found in snowflakes, coastlines, and even the branching veins of a leaf. Picture zooming into the vacuum's quantum foam with a microscope that defies all limits. At first, you'd see the usual chaos of virtual particles blinking in and out of existence. But as you magnify further, something strange happens. The foam doesn't simplify into uniformity. Instead, it reveals ever smaller structures, twists within twists, bubbles within bubbles, repeating in self-similar patterns down to scales so tiny they make atoms look like planets. This is the hallmark of a fractal, a shape that echoes itself no matter how deep you dive. The math behind this is rooted in the work of Benoit Mandelbrot, the father of fractal geometry, who showed how infinite complexity could arise from simple recursive rules. Apply this to space-time, and the vacuum's fluctuations might not be random noise. They could be building blocks of an intricate fractal geometry, where every fluctuation contains the seed of the whole. Some quantum gravity models, like those inspired by spin networks or causal dynamical triangulation, even suggest spacetime could be a fractal at the Planck scale, with dimensions that aren't whole numbers. Imagine a universe where space isn't strictly three-dimensional, but has, say, 2.73 dimensions at infinitesimal scales. A fractional reality where geometry itself becomes fuzzy. Why does this matter? Because fractals aren't just pretty math. They're nature's way of packing infinite surface area into finite space, like the lungs' branching airways or a broccoli's florets. If spacetime is fractal, it could explain baffling phenomena like black hole entropy, how these cosmic monsters store unimaginable amounts of information on their surfaces. Just as a crumpled sheet of paper hides more space than a flat one, a fractal vacuum might encode data in its folds, turning every plank-sized wrinkle into a bit of cosmic memory. The wildest implication, fractal spacetime could rewrite singularity physics. Inside black holes or at the Big Bang, where general relativity predicts infinitely dense points, a fractal structure might smooth out those infinities, replacing them with intricate, self-repeating layers. It's like swapping a broken elevator for an endless staircase, each step smaller than the last, but never truly collapsing into nothingness. Some theorists even speculate that if the vacuum's geometry is fractal, it might generate observable signatures in high-energy particle collisions or gravitational waves, tiny fingerprints of the universe's hidden crinkles. But here's the twist. Fractals are inherently scale-free, meaning patterns repeat whether you're gazing at a galaxy or a grain of sand. Could the vacuum's quantum foam echo the large-scale structure of the cosmos, with galaxy clusters arranged like virtual particles in a cosmic feedback loop? It's a dizzying thought that the universe might be a hall of mirrors, where the smallest and largest scales reflect each other in ways we're only beginning to glimpse. One thing's certain, if spacetime is fractal, then emptiness isn't just bubbling, it's folding, unfolding, and refolding itself into an infinite origami of existence. And somewhere in those folds, the universe might be hiding its most profound secrets, written in the language of shapes without end. We've journeyed through 29 mysteries: virtual particles, black hole evaporation, even the possibility of spacetime itself being a hologram. But now we arrive at the most provocative question of all. Could the quantum vacuum be aware? Not in the way you or I are, of course. But what if the seething energy of empty space carries some primitive form of consciousness, a whisper of experience woven into the fabric of reality itself? This isn't mysticism, it's a fringe but fiercely debated idea called panpsychism, and it forces us to confront what mind might mean at the universe's most fundamental level. On one side, mainstream physics treats the vacuum as a mindless, if dynamic, medium, a stage where particles dance according to mathematical laws. There's no need to invoke consciousness to explain its behavior. Quantum field theory and general relativity cover the basics just fine. But panpsychists argue that this misses a deeper pattern. From neurons firing in brains to electrons exchanging information in entangled states, nature seems to build complexity out of simpler units. If consciousness emerges from the right arrangement of matter, could its roots stretch all the way down to the vacuum's quantum fluctuations? Imagine the vacuum as a vast, buzzing network of interactions. Every virtual particle pair, every entanglement event, every fluctuation could be a flicker of proto-experience, not thought or feeling as we know it, but the barest hint of something that, in the right configurations, builds up to awareness. It's like comparing a single pixel to a movie screen. One is meaningless alone, but together they create a canvas where meaning emerges. Some theorists, like philosopher David Chalmers, suggest this could solve the hard problem of consciousness, how subjective experience arises from objective physics. If even the vacuum has a rudimentary form of mind, then consciousness isn't an illusion or accident, but a fundamental feature of reality, waiting to be unlocked by the right structures. Critics, of course, scoff at the idea. They point out that panpsychism risks being untestable, a just-so story that explains everything and nothing. Neuroscientists like Christoph Koch counter that consciousness likely requires highly specific architectures, like the neural networks in brains, not the random buzz of vacuum fluctuations. And then there's the combination problem. How could countless tiny, micro-experiences in the vacuum combine into the seamless awareness you're having right now? It's like saying a pile of sand grains inherently knows how to become a sandcastle. Yet the debate isn't purely academic. If the vacuum has any form of intrinsic experience, it reshapes how we view everything from AI to alien life. An artificial intelligence built on quantum processors might not just simulate consciousness, it could tap into a substrate where mind is already latent. Similarly, extraterrestrial life might not need carbon-based brains to be aware. It could arise from entirely different quantum architectures, all drawing from the same primordial well of vacuum proto-mind. Even wilder is the implication for cosmology. If the vacuum is in some sense alive, then the universe isn't just a cold machine. It's a process exploring its own potential, with consciousness as one of its emergent languages. This isn't far from ideas in integrated information theory, which sees consciousness as a property of any system with the right causal complexity. Under this lens, black holes, galaxies, or even space-time itself could possess shades of experience utterly alien to our own. So where does that leave us? The truth is, we don't know, and may never know, whether the vacuum harbors the faintest spark of mind. But the mere possibility forces us to ask, is the universe just a collection of dead matter obeying blind laws, or is it something far stranger? A place where nothingness brims with activity, where emptiness might, in some ineffable way, feel. As we peer deeper into the quantum abyss, we're not just uncovering the secrets of space and time. We might be glimpsing the earliest stirrings of whatever it is that lets reality look back at itself and wonder. From virtual particles blinking in and out of existence to black holes slowly evaporating into the void, we've explored 30 mysteries that reveal the quantum vacuum as anything but empty. Each one is a piece of a grand cosmic puzzle, challenging everything we thought we knew about reality. The vacuum isn't just background noise, it's an active participant, shaping the universe from the smallest particles to the largest structures in the cosmos. Think of these mysteries as threads in a vast tapestry. The Casimir Effect shows us how emptiness pushes. Hawking radiation proves black holes aren't eternal. Entanglement suggests space itself might be stitched together by invisible connections. And vacuum decay reminds us that even the laws of physics could be temporary arrangements in a multiverse of possibilities. Together, they paint a picture of a universe where nothingness is the most dynamic thing of all. What's coming next? Imagine quantum gravity detectors spotting space-time foam's graininess, or lab-made wormholes proving ER equals EPR. Picture telescopes capturing bubble universes colliding in the cosmic microwave background, or AI decoding the vacuum's hidden patterns faster than any human mind. The next decade could rewrite physics not by looking at stars or particles, but by probing the void between them. So which mystery left you breathless? Was it the holographic principle turning reality into a cosmic projection, the Dirac sees ghostly particles, or the chilling possibility that consciousness itself might ripple through the vacuum's depths? Drop your favorite in the comments. We're just scratching the surface of these enigmas together. Here's the truth the universe has been whispering all along: the vacuum isn't empty. It's the stage for existence's greatest secrets, waiting for us to pull back the curtain. And as we keep exploring, remember, every time science stares into the void stares back. With answers we're only beginning to understand.